Hello, and welcome to the Ohio DOT training for its Multimodal Design Guide, or the MDG. This video is the 10th module of a 13-part training series that will span the entirety of the guide. In this video, we will focus on Chapter 9, Multimodal Accommodations at Interchanges and Alternative Intersections. This chapter expands on the general pedestrian facility guidance provided in Chapter 4, bicycle facility design guidance in Chapter 5 and 6, and motor vehicle facility design guidance in Chapter 7, with a focus on pedestrian and bicycle accommodations at interchanges and alternative intersections. Designers should use this chapter to understand pedestrian and bicycle safety and operations at interchanges and intersections, but should consult the NCHRP Report 948, Guide for Pedestrian and Bicycle Safety at Alternative and Other Intersections and Interchanges for in-depth approaches for evaluating issues and design alternatives. Interchanges and alternative intersections are typically implemented to increase motor vehicle safety and capacity and reduce motorist delay by adjusting geometric features, signal operations, or lane utilization and configurations of a more traditional intersection. As a trade-off, pedestrian and bicycle routes through interchanges and alternative intersections often become more challenging. At interchanges, there are often multiple intersections to navigate, which may be paired with free-flowing vehicular movements, typically higher traffic volumes and vehicle speeds, and the presence of larger vehicles. The chart shown here from Chapter 4 discusses how larger roadways with higher speeds lead to lower yielding rates. While the route through the intersection or interchange may vary from a traditional intersection, it is still imperative to follow best practices for pedestrian and bicycle design guidance outlined in this guide. These practices are listed here. Consider alignments that address user comfort and sight distances, minimize or eliminate multiple threat conditions, reduce motorist speeds at uncontrolled crossings, minimize the need for uncontrolled movements across crossing facilities, and provide appropriate buffer spaces between motorists and the non-motorized facilities. If these principles sound familiar, it's because while the tools and layout may look different, the outcome is the same. At both four-leg perpendicular intersections and complex interchanges, our goals are to minimize conflict points, crossing lengths, motorist speeds, provide logical routes across the intersection, balance delay, and provide adequate sight distances. 4 interchanges are described in this section: Diamond Interchanges, Cloverleaf Interchanges, Single Point Urban Interchanges, and Diverging Diamond Interchanges. We will cover each of these and touch on some of the treatments, but this training is not intended to discuss all treatment options or evaluations available or outlined in the guide. Specific design guidance for motor vehicles at interchange facilities can be found in the Location and Design Manual, Volume 1, Section 500. Diamond interchanges are the most common form of interchanges. They allow for free flow operations on the major highway, but create at-grade intersections on the minor roadway with ramps. Because of this, the same principles and treatments for a typical intersection apply to the intersections formed at diamond interchanges. Cloverleaf interchanges often utilize free-flow loop ramps to accommodate left turn movements between the major and minor roadway. These free-flow ramps allow motorists to execute these left turn movements without traveling through an intersection and are often designed to allow drivers to navigate the interchange without stopping. Full cloverleaf interchanges use these loop ramps at all 4 quadrants, while partial cloverleafs use loop ramps in 1 to 3 quadrants and Diamond Intersections control options for the other quadrants. However, the use of high-speed, free-flow ramps runs counter to the principles of safely accommodating pedestrian and bicyclist and present challenges as listed on this slide: limited visibility, reduced yielding, and longer crossings. There are multiple treatments that can be implemented to help improve pedestrian and bicycle facilities within the interchange. For pedestrians, designers should implement high visibility crosswalks and install pedestrian warning signage, yield lines, and potentially rectangular rapid flashing beacons at uncontrolled crossings to warn drivers of the likely presence of pedestrians. Designing or reconstructing the on-off ramps from a free flow condition to intersect the crossroad at an angle closer to 90 degrees with smaller radii reduces vehicle speeds and orients the driver to directly face the crossing location. Where it cannot be modified, the figure shows how a sidewalk can be aligned to achieve a 90-degree crossing for both entrance and exit ramps. A bicycle facility should be provided and clearly marked through the free flow, merging, and diverging areas at the ramp terminal to improve visibility of the bicyclist and reduce exposure to vehicles exiting and entering the roadway. For many of the interchanges and alternative intersections, it is also recommended to provide opportunities for bicyclists to leave on-street facilities and transition to a separated bike lane or shared use path, as shown in the figure on the left. Chapter 6 covers bicycle ramp design for transitioning bicyclists from on-street facilities to side paths or shared use paths. A single point urban interchange, or SPUI, is a variation of a diamond interchange. The footprint is comprised to a single traffic signal, creating a X pattern for vehicle traffic using the interchange ramps. With this interchange, right turn movements are often a free flow maneuver to increase vehicular capacity, and only the left turns pass through that traffic signal. The biggest challenge to accommodating pedestrians at single point urban interchanges stems from the sheer size of the interchange and the resulting length of the pedestrian path of travel through the interchange, the number of conflicting signal phases, and the uncontrolled crossing locations. Pedestrians are only able to cross a portion of the interchange in a single signal cycle, and it might take as many as 4 phases to traverse the entire interchange if each crossing is signalized. Pedestrians may not desire the delay or additional effort to reach crossing and may choose to cross outside of a crossing and signal phase, risking exposure to vehicles. Bicyclists face similar challenges to pedestrians when trying to navigate a single point urban interchange due to the size of the intersection. Bicyclists might have a difficult time clearing the intersection's yellow and all red phases. Uncontrolled right turn lanes may also expose bicyclists to large mixing zones and areas of increased conflict with higher speed vehicles. As shown in these figures, the guide illustrates both the conflicts and possible layouts to address these challenges. Diverging diamond interchanges, or DDIs, are a variation of the traditional diamond interchange. These interchanges use directional crossover intersections to shift traffic on the minor roadway to the left-hand side of the roadway between the ramp terminals within the limits of the interchange. The crossover eliminates the need for a left turn signal phase for the ramp terminals. However, this presents challenges for pedestrians, especially pedestrians with vision and cognitive impairments, as the direction of the approach traffic is unexpected. Additionally, as with Cloverleaf interchanges, there are many free-flowing points that must be addressed for both bicyclists and pedestrians where crossings occur. With a DDI configuration, there is an opportunity to provide two different pedestrian routes through the interchange. Through the center of the interchange in the median within the interchange core, or along the outside of the interchange like traditional interchange configurations. Table 9.2 highlights the advantages and disadvantages of the two route placement options. For bicyclists, there are three options for DDIs: a marked bike lane through the DDI, a shared use path, or a shared travel lane. With all three of these options, signal timing should be timed to accommodate a bicyclist through all movements and phases. Additional challenges and treatment options are discussed further in the guide. In the next section, alternative intersections are reviewed. 4 alternative intersections are included in this section: median U-turns, restricted crossing U-turns, displaced left turns, and roundabouts. As with interchanges, we will cover each of these options and touch on some of the treatments, but this training is not intended to discuss all treatments or evaluations available or outlined in the guide. The median U-turn intersection eliminates turns at the main intersection on one or both of the intersecting streets, with indirect left turns using a U-turn movement located downstream from the intersection. Typically, a wide median is needed to provide separation between directions of traffic and facilitate the left turning movements. Vehicles on the minor street that would turn left at a conventional intersection will instead turn right onto the major street and then make a U-turn movement. Signals at the main intersection facilitate through and right turns. On the major street, signals can be provided at the U-turn movements if appropriate. For both pedestrians and bicyclists, strategies to mitigate the right turn conflicts are discussed. For pedestrians, designers must choose between a single or two-stage crossing. The guide discusses the trade-offs that need to be evaluated before selecting the preferred option. Similarly, the path and the expected operations for bicycles turning left from the minor roadway must be clear. There are 3 options in order of preference presented in the guide. Restricted crossing U-turn intersections eliminate left turn and through movements from cross-street approaches at the intersection. To facilitate these cross-street movements, minor street drivers are required to turn right onto the major street and then make a U-turn maneuver at a one-way median opening downstream of the main intersection. However, the island to facilitate these movements means that a pedestrian has to zigzag across the intersection, which increases delay and may force a pedestrian to cross more times than they intended if they could have remained on the same side. In addition, if bicyclists follow the same path as motorists, they are forced to merge and weave multiple times to go through the intersection. With the unique layout and motor vehicle movements at an RCUT, providing a highly visible, clearly defined space for pedestrian crossings and bicycle paths of travel is critical to both vulnerable users' safety and motorist recognition. A displaced left turn, or DLT intersection, is an at-grade intersection that relocates left turns to the right side of opposing traffic with a crossover intersection upstream of the main intersection. By moving the lefts to the right side of opposing traffic, all movements of the major street can proceed simultaneously, eliminating the need for a separate left turn phase. The goal of a DLT intersection is to reduce intersection delay for motorists and achieve higher vehicle capacity than a traditional intersection. However, this configuration and signal phasing creates trade-offs for bicyclist and pedestrian accommodations. Pedestrian movements at DLTs are often significantly longer than at a traditional intersection because they have to cross multiple vehicle lanes and medians. There are 2 typical crossing options for pedestrians at DLTs: an outside crossing, or an inside crossing. Designers have the challenge of creating a reasonable route that minimizes travel time for pedestrians in both options. For on-street bicyclists, an inside crossing with two-stage left turn boxes might be preferred. The outside crossing does not often provide a convenient or comfortable location for a two-stage left turn box between the through movement and the displaced left turn movement. Bicyclists can also be accommodated on a shared use path and cross with pedestrians in both outside and inside crossing options, as shown in the figure for both pedestrians and bicyclists. With roundabouts, entering traffic yields to circulating traffic. The circulating roadway geometry is designed to maintain low vehicular speeds, reducing crash severity for motorists in the intersection. A raised or painted splitter island is provided on all approaches to separate entering and exiting traffic. The curved geometry of the splitter island aligns traffic with the circulating roadway and promotes lower speeds for motorists entering and exiting the roundabout. Because they promote slow speeds and the splitter islands may be used as a refuge island, roundabouts are generally considered safer and easier for pedestrians and bicyclists to navigate. Treatments such as raised crossings or truck aprons can also be used where larger vehicles are present while slowing all other motorists. While the navigation of a roundabout may be easier for many pedestrians, pedestrians with vision disabilities may struggle with the non-traditional layout of the roundabout. With a traditional intersection, pedestrians with vision disabilities can generally distinguish the direction that approaching vehicles are coming from and how quickly or slowly vehicles may be approaching by sound. With the circulating geometry of the roundabout, vehicles passing the exit legs of a roundabout can sound like an approaching vehicle that then turns away. This variation in sound may be hard to distinguish from a vehicle that is actually exiting the roundabout if the pedestrian crossing is too close to the circulating roadway. To overcome these concerns and to facilitate all pedestrian movements, designers need to ensure good channelization, proper alignment, and careful placement of the crossing. The pedestrian crossing is typically placed one car length back, or 20 feet, from the yield line on the entrance leg of the roundabout. This distance is far enough from the circulating roadway that pedestrians with vision disabilities can focus on the sound of vehicles approaching or exiting the roundabout rather than the circulating traffic. The crossing should also be placed to maximize sight distances so motorists can see and stop before reaching the crossing when a pedestrian is present. The guide discusses the 3 alternative crossing alignments shown on this slide and when they may be preferred. When considering multi-lane roundabouts as a design alternative, it is vitally important to consider how pedestrians of all abilities will be accommodated. The draft PROAG section R306.3.2 states that at multi-lane roundabouts, pedestrian crossings will require a pedestrian-activated signal for each crossing stage, including the splitter island. A pedestrian hybrid beacon, or PHB, is an appropriate signalization treatment. However, these are expensive, and if overhead wayfinding signage is provided, a PHB can create additional visual clutter for motorists. Motor vehicle operations must also be a consideration when determining if a multi-lane roundabout with PHBs is an acceptable design solution and should be compared to the motorist operations if instead a single-lane roundabout were provided. To better accommodate the needs of people with vision disabilities, the MDG provides the table shown on this slide to identify treatments appropriate for various roundabout conditions. Please note that the rectangular rapid flashing beacon with audible devices are not PROAG compliant, but can enhance accessibility. Motor vehicle operations must also be a consideration when determining if a multi-lane roundabout with PHVs is an acceptable design solution and should be compared to the motorist operations if instead a single-lane roundabout were provided. Rectangular rapid flashing beacons with audible devices are not PROAG compliant, but do enhance accessibility. Typically, with a single lane and compact roundabout, it is recommended to merge on-street bicycle facilities with motorist traffic so that bicyclists travel through the roundabout in a shared lane. Additionally, the Ohio MUTCD Section 9C.04 states that bicycle lanes are not to be located within the circulatory roadway of a roundabout. While highly confident and somewhat confident bicyclists may be comfortable traversing a roundabout in a shared lane environment, many bicyclists will not feel comfortable navigating roundabouts with higher motorist volumes, especially multi-lane roundabouts. For user comfort, roundabouts should also be designed to facilitate bicycle travel outside of the circulating roadway on a separated bike lane or shared use path. Where shared lanes or bicycle lanes are provided on the approach to a multi-lane roundabout, it is recommended to transition on-street bicyclists to a separated facility. Figures and guidance illustrating how these transitions should be incorporated and what markings and signage should be provided are illustrated in the guide. Thank you for watching this video covering Chapter 9 of the MDG. For other chapters, please see the additional videos in this series.